In the next two examples, we will find the p-values. The p-value, the probability value, is the area associated with the test statistic. So in example 1, we'll let alpha equal 0.05. The test statistic in a left-tailed test is negative 1.88, and we're to find the p-value. So let's get a diagram of this. It's a left-tailed test. And what we're saying is we have a alpha of 0.05. So what I've shaded here is the area associated with alpha. Alpha equals 0.05, and of course that is the area corresponding to the critical value. And the critical value for 0.05, recall, we got that by saying inverse norm, area to the left. So I can find that. We did that in the previous video using inverse norm on the TI-83-84 calculator, negative 1.645. Okay. Well, in this left-tailed test, we have a test statistic of negative 1.88. So that would be a little further to the left of negative 1.645, negative 1.88. The p-value is the area associated with the test statistic, so it represents this area. So to find this area, recall how we find the probability when given the z-score. We use the normal CDF function, and we put in our minimum value, or where the shading begins on the left. It begins at, this goes on and on and on to negative infinity, and we said for negative infinity we will use negative 5. Of course you can use negative 999, negative 7, lots of other values will work as long as you're only rounding to 4 decimal places. Negative 5 works fine. Then our maximum value, well, we end with our shading here in the orange at negative 1.88. So when we use this function, it will give us that area associated with this test statistic of negative 1.88. So the normal CDF on your TI-83-84 calculator will give you 0.03005, and we're rounding to 4 decimal places, so that's approximately 0.0301. Recall that we had the memory trick for our decision. If P is low, HO must go. And our p-value is less than our alpha, so this is a situation where we would reject the null hypothesis. Also notice that the test statistic, negative 1.88, falls within the critical region here. That's cut off by the critical value. Remember, critical value separates the z-scores that are likely to occur, these on this side on the right, from those that are unlikely to occur. So we would reject. Let's look at another example. In this case, we have an alpha of 0.08, and what they tell us is our alternate hypothesis is that the population proportion is not equal to or different from 0.4. The test statistic is negative 1.54. So recall that the alternate hypothesis tells us which type of test we have. Not equal to is a two-tailed test. So let's see what we know. With the two-tailed test, we know we have to split our alpha. This is alpha over 2, or 0.04. And this is alpha over 2, or 0.04. Okay, so in order to know where our test statistic lies, we need to find out what these critical values are. So the critical values for 0.04, we know because of our symmetric graph that this will be a negative z-score, this will be the positive of the same z-score. Inverse norm 0.04, and we get negative 1.75 rounded to 2 decimal places. So this one is positive 1.75. Okay, we're told that our test statistic is negative 1.54. Well, that would be somewhere out here, right? Okay, and p-value is the area to the left here of our test statistic because it's on the lower side here. So the p-value starts here. Now, on a two-tailed test, what we're actually seeing here is half of the p-value. Just like this is half of alpha, we would also be looking at, I'll just use dotted line, this area here. We add those two together to get the total p-value, because this is the case where it's not equal to 0.4. It could be higher, it could be lower. And what we're told is that it's a negative, our sample that we took gave us a test statistic of negative 1.54. Okay, so we could be on this end or we could be here. So we will have to double the area we find associated with this test statistic. Okay, so to find that area, we use the normal CDF function, and we start way down at negative infinity. We'll use negative 5 up to negative 1.54. Again, this is going to give us half of the p-value, and we get 0.06177. Now I know I'm going to be rounding my final result to 4 decimal places, so I'm purposely taking this out to 5. Okay, so in order to find the p-value associated with this test statistic, I have to double the area that I found. And now is when the rounding to 4 decimal places takes place. Okay, so notice in this example the test statistic is not in the critical region, and our alpha is larger, our p-value is larger than alpha. Our p-value is about a little more than 12%, and alpha's 8%. So, and we can visually see that it's larger. We're not with like the last example where we were inside that area, we're outside that area. So this is how we can find p-values, the area, the probability associated with the test statistic.